Last time we started getting into systems of differential equations. When we think about solving a system of differential equations, and by the way, system just means multiple equations, there's two things that make it seem hard. One thing is what's happening with derivatives. So in the order of the derivative, so fourth derivative, fifth derivative, the higher the order it goes, the more challenging it is to solve. At least that's been our experience, and yeah, it's true. But the other thing is the number of equations involved. The more equations involved, it should be more challenging to solve. And so one of the things that was mentioned is that we can actually do a bit of a trade-off here, which is to say the following. We can lower the derivatives by increasing the number of equations. Now that's what we did last time. What was the idea? Suppose I have a high order derivative. Let's say y fourth derivative. So y prime 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 prime. Well, what we can do is we can introduce a series of variables. y1, which is the original function, y2, which is the first derivative, y3, which is the second derivative, and y4, which is the third derivative. And now each one of them relates step by step to the one that came before, and then at the very top, that's the derivative of the last one you introduced. So you can reduce the order, and by doing this, we can get everything down to where it's a first derivative equals something, at, of course, the challenge of more equations. But we'll see in the near future that we have ways of handling that. But there's also a different way we can go, which is to say, well, we can reduce the number of equations, but we're going to drive up the order. Now, we saw an example of this, which is we had two equations and we were able to use the idea of substitution to combine it and get it down to one equation. But in the original, we had two equations where we had a first derivative. When we got it down to one equation, it was a second derivative. The goal for today is to actually talk about a systematic way to do this. And in particular, we're going to show how we can always get down to one equation when we start with something which is relatively simple. In other words, linear, but that's all right. We love linear equations, and linear differential equations, they're the best. And so that's our goal. Let's talk about how we get there. So what we're going to need is some notation. We're going to use what we call the D notation. Now, D is shorthand for derivative. So you can say that today's lecture is brought to you by the letter D. Now, what is going on? Well, you can say when I multiply something by D, in other words, D times something, and of course you should times here in quote marks, but you could rather more accurately say D applied to Y says apply the derivative. So that would be Y prime. If I do D squared, well, how can we think of D squared? Well, D squared Y, that's really D dy, and it says, all right, just onions, one layer at a time. So dy says take the derivative of y, so that's y prime. And then you say, okay, next layer, derivative of y prime is y double prime, and so forth and so on. By the way, it doesn't just have to be y. We can have all sorts of fun. So the derivative of e to the x is e to the x. All right, well, that's not a very interesting one, but let's try some funner ones. D of sine of 2x, what would that be? Well, the answer is take the derivative of sine of 2x. And derivative of sine is cosine, and don't forget the 2, so 2 cosine 2x. And you can do more. The derivative of 5 is what? 0. Derivative of constant is 0. And you could say, what's the derivative of d cat? Well, who knows? Depends what the cat is. How does the cat depend on x? Well, all right. But anyways, the moral here is, in our setting, we can always do that. Now, why are we introducing this D notation? Well, one thing we can do is once we have it, we can rewrite these differential equations, where in particular, we're working with linear differential equations, and we're going to be restricting ourselves linear constant coefficients. So in other words, nice, but that's all right. It's okay to live in a nice world. You can say, well, you have y double prime minus 5y prime plus 4y. Y double prime, d squared y. That just, remember, that's second derivative. Y prime, dy. And then y is, well, it's just y. And now you could say, well, hey, look, what can I do with this? I have y's here, so we can start to do algebra. And it seems strange to say, wait, we're doing algebra and there's this d operator here. That's just, by the way, d operator is just a fancy word for saying there's this d that does something. And it works. It works. So, for instance, we say, okay, well, pull the y out. So it's d squared minus 5d plus 4 times y. Now, that looks like a polynomial because it is a polynomial. It's a polynomial that involves the d. And if you have a polynomial, you can do things like factor. Quadratic formula, by the way, not going to work. But factoring, that's great. You might say, wait, why not the quadratic formula? What does it mean to take the square root of a derivative? No. But what does it mean to take two derivatives? Yeah. Okay, that makes sense. D, repetition. So you can factor this as d minus 4 times d minus 1, or you can factor as d minus 1 times d minus 4. And there you go. There you go. And so this is just another way to rewrite differential equations, which gives us another way to, for lack of a better word, play with expressions. Because math should be fun. We should be allowed to play, shouldn't we? I think so. So here we go, our big idea. And we're going to do a variation of Cramer's rule. Now, underlying all of this, you should think in the background that really what we're trying to do here is elimination. That's our game that we're playing today. And so we're trying to get down to sort of one equation, or you might say one unknown function. And how does it work? Well, we ask the question, suppose we are in the following setting. So we have a matrix here. And the entries in this matrix are kind of interesting. They're not numbers, they're not functions, they're polynomials in terms of d. Now, this might sound strange, but it's allowed. So, okay, this is an expression involving d, and there's an expression involving d, and so forth and so on. And then we have x, y, and x and y are what we're trying to solve for. In other words, they're the functions we're after. And on the right-hand side, we might have functions, f of t, g, t. They may be 0. If they're non-zero, it's non-homogeneous, which is perfectly fine. So, if we're in this setup, the punchline is that we can solve and create a differential equation for x and solve and create a differential equation for y. And by the way, this isn't just for 2 by 2. This works for 3 by 3s and 4 by 4s, any size. But the reason we're working with 2 by 2s is, well, we have to start somewhere. And it's easiest for us to see what's going on. Now you might say, wait, why is this called a variation of Cramer's rule? Well, if you remember Cramer's rule, and if you don't, we're going to do a really quick 5-second recap. You might remember it was where you had numbers. So A, B, C, D were numbers. X, Y were, again, unknown numbers. And we were trying to get to E, F. Then Cramer's rule would say, well, X, that number, is really a ratio. It's a ratio of two determinants. Downstairs, you have the A, B, C, D determinants. In other words, what that matrix is. And upstairs, what you do is you say, well, I'm going to modify this by replacing a column by what my target is. Now, which column? Well, the first column goes with the first variable. The second column goes with the second variable. So the first column is the x's. The second column is the y's. So you say, oh, I replace the x's part, the f, and then I keep the other column as is. So that's Cramer's rule, which says, you can solve as a ratio of two determinants. Now, if you look at what you have here, it's two determinants, but it's not a ratio. We've taken this bottom determinant and moved it across. So if you were to rewrite Cramer's rule, it would say A, B, C, D times X is the same as E, F, B, D. And you can see, yeah, I moved it across. So why are we doing this here and not like it's there? The short answer is because it doesn't make sense to divide by an operator. It does make sense to multiply. So in other words, I can multiply by D, I can't divide by D, so I don't want to put anything with D downstairs. And that's this part, it's full of D's. And we're going to see this as we go through an example. In fact, we have an example right here. So suppose we have this differential equation, x prime, which is 4x minus 3y, and y prime, which is 6x minus 7y. Say, all right, what can we do? Well, we're going to rewrite it. So the goal here is to get it into something which matches this notation. So we're going to move everything with x's and y's to one side, everything not with x's and y's to the other. Now in this case, there's nothing except x's and y's, so the other side is going to be zeros. So we have x prime minus 4x plus 3y minus 6x plus y prime plus 7y. Now, we take each expression. When I say each expression, the x expression for each term, the y expression for each term. And we rewrite it using our D notation. So we'll have dx, 4x. So that becomes d minus 4x. 3y minus 6x. And then y prime is dy. There's 7y, so that's d plus 7y. Well, now we say, hey, that looks a lot like the kind of thing we're used to when we're solving with matrices. Namely, we have a system of equations, we have coefficients, we have what we're shooting for. So we put our coefficients in our matrix. So that's the d minus 4, the 3, the minus 6, the d plus 7. We have what we're trying to find, the x, y, and we have our right-hand side of zeros. So the punchline is d minus 4, 3, minus 6, d plus 7. So the determinant of this matrix is equal to the determinant where we place the x column with the 0 column. Let's see what this would turn into. What's the translation here? Well, it becomes the following. This would be d minus 4 times d plus 7. So we're down the diagonal. Subtract negative 6 times 3 times x. Now here, 0 and d plus 7, well, times by 0, hard to recover, 0. And then subtract 0. That equals 0. And, well, okay, so that's d squared. And what else we have? We have 7d, subtract 4d, so that's 3d. And then we have minus 4 plus 7. It's minus 28. And here we have minus 18 is plus 18. All right, so that becomes d squared plus 3d minus 28 plus 18 is minus 10x equals 0. Or we can go one more step. D squared x, x double prime, dx, x prime, and 10x is 10x. So we've gone down to one equation for x. So that's what we've done. Now, what was our goal? Our goal was we started with two equations that were both first derivatives. We got down to one equation, which was second derivatives. All right, so fewer equations, more derivatives. That's all right. That's what we want. And so now we say, aha, this is something that we have tools for. Now, as of right now, this probably is like magic. Why does it work? And I just don't want you to say, well, it's just more magic that mathematicians came up with. It really is doing something that makes a lot of sense. So let's think about elimination that we're used to. So I'm going to come back to this equation here. So let's think about what's going on. We have d minus 4 times x plus 3y equals 0, and minus 6 times x plus d plus 7y equals 0. Now, when we think about elimination, where we have two equations, two unknowns, the way we think about it and the way we do it is we say, well, let's multiply the first equation by something, we'll multiply the second equation by something, we'll combine, and whoosh, like magic, but it's not magic, things cancel. Okay, so looking at this, what would we like to cancel if we wanted to end up with the x's? Well, if we wanted to end up with the x's, we'd like to cancel the y's. So our goal right now is to combine in a way that cancels y's. And we say, well, the problem here is they have different coefficients. So we say, no worries, we can fix that. How do we fix that? Well, we take a look and say, let's make the coefficients match. So here, there's a d plus 7, here's a 3. So let's multiply the first one by d plus 7. And in a similar, let's multiply the second one by a 3. Okay? So if we did that, because remember, we can treat d plus 7, we can multiply just like we would think. We'd have d plus 7 times 3, we'd have 3 times d plus 7. Those are the same. They're the same. Now, after you do this multiplication, and they're the same, well, what we can do is we can subtract. All right, so what do we have? Well, we have d plus 7 times d minus 4. And that's here, subtract 3 times negative 6. Now that's with the x's. Then we have d plus 7 times 3y. We subtract 3 times d plus 7y. Cancel the y's by design. That's elimination. We're eliminating the y. On the other hand, we get 0, subtract 0, which is 0. Now, does this expression look familiar? Yeah, it's essentially the same as this expression. Other than, well, okay, change the order. But besides that, it's the same. And so that's what's going on. It's making that process mechanical. And so, in other words, we don't have to think very hard. We just say, okay, plug it into the machinery and it'll work. So it's a little bit of a black box, but it's one that we can open up and say, oh, it's just going through and eliminating a variable by finding the right way to multiply, and then things cancel out. And that's something that we can get on board with. So let's look at the following example. So we're given that x double prime is equal to 5x prime minus 2y prime plus y plus t cubed. And that y prime is equal to x prime minus 3x plus e to the t. So we have a system of two equations involving x and y. And this is really the kind of system we're interested in, where we have x and y are interacting because we see x and y in both equations. So we say, okay, what's our goal? Well, we want to find a single differential equation, one equation to rule them all. And in particular, which is satisfied for x. So we currently have two equations, both involving x and y. We want to get to one equation which only involves x. So we're here to eliminate y. Now when you look at this, you say, oh, I see a way that this could be done by substitution, and it's true. Because we have this equation which has a single y. So we could say, oh, I could substitute this y prime into there. That's good. How do you do that? This next one, well, great. No problem. After you've done the substitution, take a derivative, and this will become a y prime and substitute again, and life is good. And it would work. But we wouldn't learn as much by doing the process. So we're going to go through the process of elimination, because there are times when substitution won't work very nicely. All right, so what do we do? Well, since we're starting this, let's actually talk about the process. So the first thing we want to do is we want to rearrange. And that says what? Well, we're going to rewrite it in a very convenient way for us to work with it. Now, when we're doing this, we want to put all the x's and y's on one side, anything left over on the other. Well, we have leftover parts, this t cubed and this e to the t. That's the stuff we're not going to move over. And when you're rewriting, it's good to put the x's together and the y's together. So, as an example, what will happen here? Well, we'll start with the x's. We have x double prime. And this comes over minus 5x prime plus 2y prime minus y. The t cubed stays on the other side. All right, now the next equation, start with the x's. Okay, so it's going to be minus x prime plus 3x plus y prime equals e to the t. All right, so this is what we mean by rearrange. Okay, now that we've done that step, we're ready for our next step. So our next step is to rewrite using our d. And so we want to introduce our d notation. Now remember, d for derivative. And so it's like Cookie Monster would saying, d is for derivative, it's what it means to me. D is for derivative, it's what it means to me. D is for derivative, it's what it means to me. Derivative, derivative, derivative starts with d. So, okay. So when we look at how to rewrite, just remember the number of derivatives, that's how many d's we need. So if it's a fifth derivative, 5 d's. If it's a third derivative, 3 d's. First derivative, 1 d, and so forth and so on. So here we go. X double prime, second derivative. So d squared. X prime is 1 derivative. So minus 5d and x. Okay, next part, plus 2 first derivative, d, and minus 1 y. Okay, second equation, we're going to have minus d, because there's a derivative, plus 3x, plus, here, there's a derivative, only a derivative, so dy. And the other side, we're not doing anything to right now. All right, so there we have rewritten with our d notation. And when we write this in this notation, we say, oh, it looks like you kind of have 2 equations, and you have 2 unknowns, x's and y. We do have 2 equations with 2 unknowns. And so we're like, aha, we're going to use our technology. All right, now the next step is I want to rewrite this as a matrix. And this just helps emphasize what's going on. And so put into matrix. And this is something that we're going to be working on quite a bit as we go into the next few topics. So we want to get comfortable with it. And so when we talk about putting into a matrix, we say, well, we're going to grab the coefficients of what it is we're looking for. So in this case, the coefficients are things involving d. So we have d squared minus 5d minus d plus 3 2d minus 1 d. And we're looking for x and y. And this is going to output t cubed e to the t. All right. And so that would be what it looks like in a matrix form. And you should see, like, okay, yeah, coefficients are coming down. And in particular, notice how the x, that's attached to these coefficients. So the first column, that's our x column. The y is attached to these coefficients. So the second column, that's our y column. All right, so now we have it in matrix form. Okay, so now we're ready to do our next step. So our next step is we're going to do Cramer's rule. Now remember, it's not quite exactly Cramer's rule, but we're carrying out our elimination. Okay, so what do we have? Well, we're after x. And so we are going to say determinant d squared minus 5d minus d plus 3 2d minus 1 d times x. So determinant times x. is equal to, now, we're going to take this and modify it. We're going to use this column here to modify. And now we say, well, we're solving for x, so we're going to replace the x column. Well, this is our x column. So that says t cubed e to the t 2d minus 1 d. All right, good, good. Now, what are we going to do? Well, once we have written this, of course, the next thing is, take your determinant. All right, great. So we're working right now inside our Cramer's rule. Really, that means elimination. Okay, so for our determinant, of course, remember, we have to go in our diagonals. And we're going to be doing that on both sides. All right, so what do we have? Well, we have the following. Give ourselves some space here. We're going to take d squared minus 5d times d, subtract minus d plus 3 times 2d minus 1 x. Okay, that's that side. Equals, okay, now here, t cubed d. Now we put the d part first. So this is d t cubed, and then subtract 2t minus 1 e to the t. All right, there we go. Okay, now what are we going to do? Well, mostly after this, we're going to expand and be very careful here. So this is a chance for us to flex our algebra muscles. And okay, great. So here we go. Carefully, carefully. We have the following. D squared times d. So that's d cubed. Minus 5d times d. Minus 5d squared. And then we're going to subtract minus d times 2d. Okay, that's minus 2d squared. Minus d times minus 1 plus d. 3 times 2d. 6d. 3 times minus 1. Minus 3. Okay. X. All right, on the other side, let's go ahead and get to work. A little bit, we'll do dt cubed, and we'll subtract and multiply this in. 2d e to the t, subtract e to the t. All right, back to this side. What do we have? D cubed minus 5d squared, subtract minus 2d squared. So that's minus 5 plus 2. Minus 5 plus 2 is minus 3. We have d and a plus 6d. That makes 7d. So we're going to subtract 7d. And minus makes a plus. So plus 3. And all of that times x. And while we're here, we'll go ahead and work this through. dt cubed, derivative of t cubed, 3t squared. Minus, well, the derivative of e to the t, 2e to the t. And then subtract e to the t. All right. Now, our last thing, and probably we'll go ahead and make a note here. Oftentimes we'll just get into the, momentum will carry you at this point. But of course, put back in terms of x prime, x double prime, so forth. Okay? So in other words, write it as you would normally. remove the d notation. So what do we have? Well, d cubed x is x triple prime. D squared x is x double prime. Dx is minus 7x prime. And then 3x is 3x. On the other side, 3t squared. 2e to the t, subtract e to the t, will be e to the t. So we'll end up with minus e to the t. And what do we have? There's a single differential equation only involving x. In other words, we've got rid of the y. We eliminated it. And so that is our answer. And the good news is we don't have to solve. And that's really good news, because that would take us a while to solve that. And so that's all right. That's all right. And there you go. That's the process. And once you get the hang of it, it's not bad, right? It works itself out. And the nice thing is that Cramer's rule, you don't have to think too hard about elimination. It says just put it into the machinery. That runs the elimination for you. And so mostly it's just set them up, knock them down, and life is good. This brings us to our final problem. And I don't want to say that just because it might do us in, but this really is the final problem for today. And it's going to stretch us. That brings us to our final problem. Hopefully that doesn't mean it's going to do us in, but it's going to be a good stretch, and we're going to see some intricacies that can pop up. So find the general solution to x double prime minus 3x prime minus x plus y double prime plus 2y prime plus 3y equals 0. And x prime minus x plus 2y prime plus 3y equals 0. Now here we see we have, of course, our two equations, two unknown functions, x and y, and we're trying to say what are the solutions. Now when we talk about the general solution, we have to really say, look, it's not like we're solving for x, it's not like we're solving for y, we're solving for both x and y. So in other words, what is x and what is y? And so we have our work cut out for us. So where to begin? Well, can we do substitution? The punchline here is no. Because if you look at these equations, there's no equation which has one y or an equation which has one x. You could try to get some cancellation, and you can chip away. You can, for instance, take the difference and you get y double prime just in terms of the x's, but my goodness, that's going to get challenging. So this is not a problem meant for substitution. That's all right. Not everything has to be. We have a tool for today, elimination. Let's use our tool. Now the good thing is that they've set us up for success. And by that I mean they've already put all the x's and y's together. That was so nice of them. So we can go straight into rewriting this in our notation with d's. So let's start with the first equation, the x's. The x double prime, second derivative, so d squared. There's an x prime, that's the first derivative, so there's a d. Remember the coefficient. Here there's no derivative, so we don't need any d. We do need the coefficient, so x. So d squared minus 3d minus 1x. Good. Go to the next. All right, second derivative, d squared. One derivative, 2d. No derivatives. Plus 3, and all times y equals 0. All right, moving down to the next equation, we'll have d and minus 1 times x, and then we'll have 2d plus 3 times y. All right, so at this stage, I like to write it in matrix form just to emphasize what's going to be happening. So in matrix form, this is our d squared minus 3d minus 1, d minus 1, d squared plus 2d plus 3, 2d plus 3, x, y equals 0, 0. So coefficients, that's the first piece. What we're trying to find, that's the next, and what we're shooting for it to be equal to. Now, the good news is, of course, the right-hand side is zeros. Oh, we love zeros, and that's going to make things a little bit easier, and hopefully enough that we make progress. So, remember, we have to solve for both x and y. Which one are we going to solve for first? Well, since we have to solve for both, it doesn't really matter. Just pick one. Let's start with x. Happens to come earlier in the alphabet. No really good reason, but it's something. So we're taking the determinant of the coefficients. And so I will say you'll notice these problems, they take a lot of space. They don't really necessarily means that you have to do a lot more thinking. It's just a lot more bookkeeping. And so as you do these problems, you're going to think like, oh, these problems are so long. That's okay, but don't conflate the idea of length and difficulty. They are different from each other. You can have problems that take a while, but the individual steps aren't too bad. And then you can have problems which are very short. And oh, killer. So, all right. Now, the left-hand side is pretty much automatic. The right-hand side, you have to think a little bit. Where do the zeros go? Well, since we're solving for x, they should replace what the x's were attached to. And the x's were attached to these coefficients. So the first column is the x column. The second column is the y column. So 0, 0. And we have our d squared plus 2d plus 3 and our 2d plus 3. Now, the good news is it's really hard to recover from 0. So in other words, take 2 times the derivative of 0 plus 3 times 0, 0. Second derivative of 0 plus 2 times the first derivative of 0 plus 3 times 0, 0. And so as soon as you get a column of zeros, happy days, 0. All right, so all the work is over there on the left-hand side. All right, well, that's okay. We have to do it at some point. So let's start getting into it. So we have our 2 by 2 determinant. So we're going to have d squared minus 3d minus 1 times 2d plus 3. Subtract, and d minus 1 times d squared plus 2d plus 3, all times x, and we already know that equals 0. Okay, so now algebra. We're foiling. Well, it's a little bit more than foiling because there's more than 2 terms in some cases, but we remember the philosophy of foiling. Each with each. So in other words, of each one of these 3 terms, we'll get mashed up with each one of these 2 terms. So that'll be 6 combinations. And we just be careful and take our time. No points for getting done quickly, points for getting it right. So d squared, 2d, that's 2d cubed. D squared, 3, that's 3d squared. Minus 3d, 2d, well, that's minus 6d squared. And I'll put it right underneath here just to help me keep track of the d squareds with the d squareds. Minus 3d times 3, that's minus 9d. Then we have minus 1 times 2d, that's minus 2d. And minus 1 times 3 is minus 3. Okay, so those are those pieces. Subtract. All right, d times d squared, d cubed, d 2d, 2d squared, d times 3, 3d, minus 1 times d squared is minus d squared, minus 1 times 2d, minus 2d, minus 1 times 3 is minus 3. Okay. All right. Now, We're getting a little bit tight for space, but I think we'll solve for x. I'm feeling pretty optimistic about solving for x. All right. So what do we have? We have, in the first one, 2d cubed minus 3d squared, right? 3 minus 6 minus 11d minus 3. Okay, subtract d cubed. 2 minus 1 makes plus 1d squared. 3 minus 2 makes a plus 1d, and then a minus 3 times x. All right. Now, putting this all together, 2d cubed minus d cubed gives us d cubed. And then minus 3d squared minus d squared minus 4d squared. Minus 11d minus d minus 12d. Minus 3 minus minus 3, 0. Oh, nice. We caught a break. X equals 0. All right, good, good. Now, next thing is to say, well, what is this really telling us? The differential equation for x. It's x triple prime minus 4x double prime minus 12x prime is equal to 0. All right, so now we're back into familiar territory, into something that we feel pretty good about. So we say, okay, let's take off our systems hat, let's put on our constant coefficient hat, and we're going to solve it. And so our first step is we turn this into an algebra problem. R cubed minus 4r squared minus 12r equals 0. And before we keep going forward, you might be saying, when you compare this polynomial that we just wrote down versus this polynomial, which we had in terms of d, they look suspiciously similar. Really, really suspiciously similar. Because they are. They're the same. Only thing that's happened is r's versus d's. And so it's not so surprising. There's beautiful connections going on here. Okay, that was an aside. Let's keep moving forward, because there's still a lot of work. We haven't even started touching y yet. So this is going to be a 2-page solution. 2 pages. Wow. All right. So what can we do? Well, we've lived a good, clean algebra life. So nice things have happened. We can pull out an r. And now, there's this factor. Well, we need 2 things multiplying to negative 12, but add to negative 4. So what about negative 6 and 2? Let's see. Does that work? So r minus 6, r plus 2. So that would be, well, r squared. 2r minus 6r is minus 4r, and minus 12. Oh, it does work. So our roots are 0, 6, and negative 2. All right. So there are our roots. Now, what does that tell us? It tells us the solutions that correspond to this differential equation for x. And in particular, we come to the conclusion x is e to the 0t means a constant, so just some constant times 1, plus some constant e to the 6t, and plus some constant e to the minus 2t. All right, there we go. There is our x. Whew! Nice, nice. And we're halfway. And so we just have to find y. Some good news. I don't want you to panic and be like, oh my gosh, we're only halfway. This is going to take forever. It'll take some time, but I want us to celebrate our success. You should celebrate your success. You've been amazing. We're going to keep at it. And okay, so what's going to happen with y? So we'll grab our next piece of paper. Don't worry, all grows on trees, it's renewable, and say, well, if you think about y, we have the same setup, right? So not much different happens. Namely, we're still going to have this d squared minus 3d minus 1, d minus 1, d squared plus 2d plus 3, 2d plus 3, y. There is a little change here in that the zeros aren't the first column, they're the second column. And so we have our d squared minus 3d minus 1, d minus 1, 0, 0. But good news, that is still nice. And here, it's still going to work out the same. So this is still going to become d cubed minus 4d squared minus 12d. Because nothing is different. And so this determinant simplified to that expression. It's still going to do that. And so we're like, oh, well, that means we're still having the same differential equation for y, which means that for x, we had this expression, so y is going to be similar. So at this point, we could say, okay, what happens? Well, we know x looks like a plus b, and I'm just going to double check because I'm paranoid, b e to the 6t, c e to the minus 2t. So a plus b e to the 6t and c e to the minus 2t. And y is going to be similar, more constants. So some constant d, capital E, e to the 6t, and f, e to the minus 2t. All right, good. Now, are we done? And why not? Okay, so the answer to the first question, are we done, is no. One of these times I really wish the answer was yes, but you know, we want to make sure we've answered it fully. Now you might say, well, wait, you've solved for x. We did. You solved for y. We have. So haven't you solved for both? Well, that's the thing, is that x and y relate to one another. That means that these coefficients also relate to one another. So we really don't have 6 different coefficients. We really should have like 3. And so, in other words, how do these connect? So that's the question. So how can we figure it out? Well, the good news is we know how x and y relate to each other because they relate via these equations. So we'll pick one. And let's pick this one. Now you might say, why? It's shorter. Okay, I can go with that. And so we're going to plug into here and see what happens. Okay, so here we go. And so we're making some notes just so we know where we're going. Our final goal for what we need, find how our constants relate. And the way we're going to do that is we're going to plug this in to x prime minus x plus 2y prime plus 3y, and remember that equals 0. All right, so here we go. X prime. Well, take the derivative. Derivative of constant is 0. Derivative of b e to the 6t, 6b e to the 6t. Derivative of c e to the minus 2t, that's minus 2c e to the minus 2t. So x prime minus x a plus b e to the 6t plus c e to the minus 2t plus 2 y prime. Okay, derivative of constant is 0. Derivative of e to the 6t, well, the 6 comes down. 6e e to the 6t. Here, the minus 2 comes down, so minus 2 f e to the minus 2t. So that's our 2y prime. And then plus 3 y. So that's d plus e to the 6t plus f e to the minus 2t. All right, we fit. Barely, but you know, that still counts. All right, I'm going to move this up a little bit here. And, oh, not too far. There we go. So, now we're going to gather. This might be feeling a little bit reminiscent of like, oh, isn't this kind of like what we were doing for undetermined coefficients? Yeah, it really is. See, in undetermined coefficients, we had some unknown constants and we plugged them in and we said, oh, here's what they need to do. We're doing a similar thing in that, like, oh, we have these coefficients and we plug it in to say, well, how do they relate? So we're going to gather by the function type. So there's the function 1. All right, so we're looking for 1. So there's a minus a, don't forget that, distributes through, and a plus 3d. Okay, minus a plus 3d. All right, and then we'll go e to the 6t. Well, we have 6b. Here we have minus b. Don't forget the distribute. Here we have 12e. And here we'll have 3e. All right. And then we're going to have our e to the minus 2t. And what's going on here? Well, we have minus 2c, minus c, and then we'll have minus 4f and plus 3f. All right, great. Now, what needs to be true? Well, what needs to be true is each one of our coefficients has to be 0. So we say, well, each one is 0. And we get a system of equations. Now, the question is, should we solve for D, E, and F in terms of A, B, and C, or vice versa? I would say, let's solve for everything in terms of A, B, and C, just because it came first. Nothing stronger than that. But all right, so here we have minus A plus 3D equals 0. That says A equals 3D, or we could say D is 1/3 A. All right, how about here? This becomes 5B plus 15E equals 0. And so we could say, well, 15E is minus 5B. All right, so E, when we divide, minus 5 over 15 is minus 1/3. Okay, so minus 1/3. And here, well, we have minus 3C, and then here, minus F equals 0. Our F is minus 3C. So, what does that say? Well, it says if X is A plus B e to the 6t plus C e to the minus 2t, then Y looks like, well, D, which is 1/3 A, E, which is minus 1/3 B e to the 6t, and F, which is minus 3C e to the minus 2t. And there we go. So this is the solution for X and Y for our system. Whew! That was a workout. And you know, it takes some time. But I don't want you to be overwhelmed. Okay? There was a lot that happened, yes. We did what? We did elimination, got a differential equation for X, solved for X. We said, oh, it's the same solution for Y, different constants. And we said, okay, plug in and find how our constants relate. So there's kind of a couple big steps, but each one is manageable. It just be patient, do the work. You can do this. I believe in you. Thanks for sticking around. Thanks for being so patient. And I hope to see you again soon. Bye.